Hey everyone, this is part 2 of a 3-part video on the related rates unit. And we're going to start this video looking at the same guidelines that we looked at in the first video, and that is the 5-step procedure you want to kind of follow generally when you're solving one of these problems. And drawing a picture first, listing out all your knowns and your unknowns and variables, then creating that relationship. That's probably the most important step here. From there, substituting any constant values. These are things that in the different snapshots are not changing over time. And then at that point, once those constants are in, you differentiate and substitute and solve from there. So we're going to do 3 examples in this video. And the first one is a little bit of a review of the last video, but it has Pythagorean theorem just in a different context that may not be as familiar to you. So in this case, we have ourselves a winch with an altitude of 20 feet, and it reels in a rope at 2 feet per second. How fast is the boat moving when the rope is 45 and 22 feet? And I wanted to pull this one up just because these questions with like a boat at a dock and being pulled in uses some of the terminology you may not be familiar with. So we have our dock here, okay? And a winch is just essentially, I'm going to oversimplify this here. It's essentially a rope mechanism, a reeling in of a rope. It's like a machine typically that reels in a rope for a boat that's out in a lake or ocean or whatever it might be. So there's your winch is this thing right here. And so what it's doing is it's pulling this boat in. The boat is in the water, of course, so the altitude here being 20 feet, and this is going to be important for this, is a constant value. No matter where that boat is located, as it's being reeled in, as that boat gets closer and closer to the dock, it's going to end up still being an altitude of 20 feet to the dock. So with that being said, this is also a Pythagorean theorem. What are some things that are changing? Well, this value of x is changing. This is how far the boat is from the dock, as well as this, we'll call it z value, which is going to be the length the length of the rope here, okay? So let's go through the problem and read through. So the winch has the altitude of 20 feet. That's our constant value. I already went ahead and labeled that. It reels in a rope at 2 feet per second. Now, because you're reeling in the rope, that's the rate of the rope. So the rate of the rope is going to be dz dt. It's the rate of the z, which I'm calling the rope here. And so it's going in at 2. Now, it's reeling it in, which means that the z value is getting smaller. So it's really important to note here that since z is getting smaller, this would actually denote a negative rate. So now our question we're going to ask here is how fast is the boat moving when the rope is 45 and 22 feet? How fast the boat is moving is actually going to be its horizontal rate of change, aka the x value. How quickly is it moving towards the dock? So this is asking us to find dx dt, and that's sort of our question mark. Some of the other variables that are put in this problem, they want to know when the rope is 45 feet and 22 feet. So why don't we look and do one example of that together? We'll do the 45 feet first. That's an x value. That's a z value. The rope is actually the z. So z equals 45. So as mentioned, this is a Pythagorean theorem. It's a right triangle. So this is going to be x squared plus, now the 20 is a constant, so it's 20 squared equals z squared. We can go ahead and set that up. Recognize that the x and the z are going to be changing in the different snapshots as the boat is getting closer to the dock, but the 20 is not going to change. So what we're going to do now is we'll take that derivative. So 2x dx dt plus 0 equals 2z dz dt. And all we have to do now is we have to plug in the different values. So we're going to get 2, and our x value here is not known. So we'll come back to that. Dx dt is also unknown. So there's a little bit of a problem we're going to have to discuss. The z value is 45, and our dz dt is -2. So like the last problem in the previous video, we have a missing side that we don't know, and that is x. We can find x, however, by doing the Pythagorean theorem. Since we know x squared plus 20 squared equals, and then again, at this snapshot moment of time, z is 45 squared, we can go ahead and solve this problem. So when we go ahead and we do that here, and we'll just kind of speed things up here. So the x value when you do the Pythagorean theorem here that I get when I solve this ends up being, 40.311. So we're actually going to go ahead and we're going to plug that in, 40.311. Plug that in, and now we're solving for dx dt. I'm just going to go ahead and throw this in my calculator. So the part that's highlighted here in yellow, I would crunch that, and then I'm going to divide that by this number, which is like 80 point something. And so when I divide the yellow by the blue, we're going to get a dx dt value here of -2.333, 3 decimal places, feet per second. And that's going to be my final answer here. So as your own exercise here, and I'll have you pause the video for this moment, Go ahead and solve the 22 feet and see what you come up with. And here's the work for when the rope is 22 feet. Now, both answers we get for dx dt are negative. That should make sense because the boat is getting closer to the shore, so it's going to have a negative rate. The last thing I want you to note is that when the rope is shorter, so 45 versus 22, it's actually going faster because it originally was at 2.3 feet per second. At 22, when the rope is shorter, it's moving faster, so it's at 4.8 feet per second. So that's our first example. And our second example in this video is also Pythagorean theorem, but in this situation, we're going to have a little bit more of a challenge. And for this, there's actually going to be a link here that we can take a look at. So at noon, a ship is 150 kilometers west of ship B. A is sailing east, so that's going to be to the right if we're using a compass. And ship B is sailing north, so that's going to move up on my screen. How fast are the distances changing here between the two boats? So I'm going to press play here, and we can go ahead and take a look at what's happening in this problem. So you can see the one boat's going to the right, one boat's going up, and when this visual is happening, it's creating another right triangle. What makes this problem different is all the Pythagorean theorem problems we've shown you so far in these first two videos, one of the sides is a constant. Even in the winch problem, one of the sides was a constant. But in this case, all three sides are changing. They're all, even though if I press pause, that's a snapshot, they're changing and they're variables here. So that's what we're going to look at when we draw this problem out. So let's go ahead and let's draw this. So we have ship A, my drawings aren't too good here, and then we're going to have, this is B here, okay? So we'll go ahead and we'll call this X, we'll call this Y, we'll call this Z. So we can already establish the relationship is X squared plus Y squared equals Z squared. So that's going to be the place we're going to start with here. Now, I sort of did this out of order because we came up with the relationship. That's actually step 3. It doesn't matter if you go out of order. So step 2 is let's go ahead and come up with some of the information here. So ship A is 150 kilometers west of ship B, but I want to keep in mind that that's at noon. That's at 12 o'clock. So we're going to go ahead and look through some of the other knowns here. So the ship A, which is the one along the x-axis here, is sailing east at 35 kilometers per hour. So that's going to be the change in x with respect to t. The x value, as you saw in the visual, was getting smaller, so we're going to go ahead and call that a negative rate, so negative 35. The next thing we're going to do is we're going to look at the ship B, which is sailing north, and this is going to be at 25. So when we're going north here, that's going to be dy dt. I'll make sure I change that. And now the y value was getting bigger in terms of our triangle here, so we would call that positive 25. What they want us to find here, and I'm going to move this out of the way here, what they want us to find is what dz dt is. So that's going to be our unknown. There's one little problem though. We don't know x, y, or z is. So we're going to have to get a little creative here, okay? So at noon, if this was 150 kilometers, what's it going to be at 4 o'clock? What is the actual x value here? What is the y value? What is the z value? We're going to need to find all of these because when I actually go ahead and I take this derivative, and I'll do that over here real quickly, it's 2x dx dt plus 2y dy dt equals 2z dz dt. And the problem that we're stuck with now is we have 4 things that are unknown. We're only allowed to have one unknown. So in order to find x, y, and z, we have to get creative here. So I'm going to have you pause here to see if you can think about this idea. My hint here is think about that distance always is equal to rate times time. Okay, so here's some of the work played out here. And so using distance equals rate times time, keep in mind that the original time at noon, we'll go back to 0 here on the visual, okay? Ship A was 150 kilometers from that right angle, and ship B was 0 kilometers away. It was actually at that intersection point there. So I went ahead and noted that at 12 p.m. that x was 150, and at 12 p.m. the y was 0. Using distance equals rate times time, since the rate was negative 35, right, it's decreasing, times that by 4 for 4 hours, that means boat A traveled to the right 140 kilometers, which means there's only 10 kilometers going to be left at 4 o'clock. As for y is just traveling north at the 25 over 4 hours, so that means it moved 100 kilometers. So x is 10, y is 100, z was found through the Pythagorean theorem, so a squared or x squared plus y squared equals z squared. Upon solving this, we get that to be 100.5. From this point forward, this is just a matter of plugging and chugging. So I'll have you pause the video one last time for this problem to see if you can go ahead and wrap up the rest of the problem. Okay, and here is the work from everything plugged in. So again, I use my values of x, dx dt, there's y, there's dy dt, there's z, and then of course I'm solving for dz dt. And at this point, like I said, most related rate problems are calculator-based, so this would definitely be a problem that you would just crunch in your calculator and go through the arithmetic to get our answer. We get 21.393 when we solve this equation for dz dt. Z is in kilometers, T is in hours, so it's changing at 21.393. So a good interpretation here is that the distance between the boats is increasing at a rate of 21.393 kilometers per hour. So same process as the other Pythagorean theorems, just a little bit more arithmetic because there's more variables to contend with. So that brings us to our final problem on this video, and that is a cone problem. And in this situation, we have water is flowing into a cone with a height of 16 and a radius of 4 centimeters. So we're going to go ahead and we'll draw this out. The radius is 4. The height of this cone is 16. And it's going in at a rate of 2 cubic centimeters per minute. So that's going to be dV dt. So that's going to be, and it's flowing in, so it's going to be a positive 2. So the volume for this, and that's the relationship we got to look at, volume is going to be 1/3 pi r squared h. Now, as we go through this, this is really important to note. They want to know how fast the water level is rising when the height is 5 centimeters. So the height is going to be 5. We don't have a lot of variables considering that we're going to end up having a v and a dv dt, an r and a dr dt, and an h and a dh dt. So this brings us to a point where if I were to go through and actually take this derivative, I would end up with something kind of nasty that has r's and dr dt's, h's and dh's dt's, and we wouldn't have enough information based on what I have here. We can find the radius. The radius can be found when the water is 5 deep because we can actually do a similar triangle here. So this part that I'm coloring in blue would be the water. And so if we know the water's height is 5, we can actually set up a proportion here. And this is going to be kind of where this draws in. 4 to 16 is the height, which means that the height is always 4 times whatever the radius is. So we can now set up a proportion 4 over 16 equals the height of the water is going to be 5. So what is the radius going to be? So in this situation, we would have 4 times 5, which is 20. 20 divided by 16 gives me 1.25. So that's actually going to be what my radius is. But in order to do this problem, we might need to, in order to take the derivative without using a dr dt, because we don't have that, let's more generally look at this. As opposed to thinking about this as r over 5, if I call this r over h, and if we solve this for r, meaning I want to get r by itself so I can substitute it, this means that 1/4 of h is equal to r. I multiply both sides by h. If I take this relationship that the radius is always going to be 1/4 of the height, and I substitute it in, I get a new volume formula, which is 1/3 pi. This now becomes, we'll just call it h over 4 squared times h. And if you simplify this up a little bit, okay, we're going to get h squared over 16 times h. V equals 1/3. We're not taking a derivative yet. Keep that in mind. 1/3 pi h cubed over 16. Ladies and gentlemen, this is a derivative that you do not need to use the product rule with, and it is a volume formula in terms of the height. So that is now going to be allowing us to solve this problem. So looking at similar triangles here is the way that we're going to be able to eliminate one of the variables since we didn't have all the given information here to help us solve this. So from this point of the problem forward, what I want you to do is once again, pause this video, and I want you to take the derivative of this volume formula, 1/3 pi h cubed over 16, and see what you come up with. Okay, so one thing I'll add here, and I've partially done the problem for you here, is I went ahead and just multiplied the 1 over 16 that was down here with the 1/3, and I got that to be 1/48. So this case now, there's no rule, it's just the power rule, because 1/48 pi is just a constant. The derivative of h cubed is 3h squared. So notice the 3 goes here now. There's the h squared. And I wrote dh dt. Notice I only have 3 variables, and that's a good thing, because if I go over here, I have dv dt. That's a 2. So we'll go ahead and plug that in. We still have the 3 over 48 pi. We know our height was 5 because at that snapshot, at that moment of time, it's going to be 5. And then we have our dh dt. So upon, again, number crunching all of this stuff, we would multiply all of this stuff together that I'm circling, and I'll highlight in yellow. We plug all that in and divide that by 2. So it'd be 2 divided by that number. And our final answer here would be, and if you're following along here, be 0.407 dh. So h is centimeters, time is in minutes. And so that's going to be my change in my height. Again, if we're looking at the sign, that means that the height is increasing. That should make sense. at 0.407 centimeters per minute.